In this video, we're going to use some titration information to solve the concentration of silver nitrate in an unknown container. So silver nitrate is a useful antibiotic material. These days, when babies are born, we usually put erythromycin antibiotic in their eyes, but in situations where antibiotics aren't available, distant hospitals or places without good electrical grids to keep refrigeration, silver nitrate can work and has historically been an effective antibiotic for this. Infant blindness was a serious problem in the past. Being able to prevent it with some antibiotics was desirable. But your solution of silver nitrate needs to be about 1.5% by weight. Problem is, when people would mix these solutions up, if it started evaporating water over time, well, the silver nitrate doesn't evaporate, so it would just concentrate. And a bottle that had at one point weeks earlier been the correct percentage now would be a lot more concentrated. If used at that point, it could cause damage to the infant's eyes or turn them black, as silver nitrate tends to dye the skin. As a result, you'd want to test, if you didn't know, if this bottle was good or if you needed to let it evaporate all the way, collect the silver nitrate, and remake it. So in this case, let's find the molarity of that silver nitrate. Well, we use 100 milliliters, so 0.1 liter of my silver nitrate solution. To that, we're going to add some sodium chloride solution, and drop by drop, we're going to add it here. Build up a little bit until we see the solid stop forming. What we found is that I had to drop the volume by 32.7 milliliters in order to react all of the silver nitrate. Every drop hits, I made a little bit of solid. The solid settles to the bottom, but eventually the next drop doesn't make any solid. The idea being we've used up all the silver, so more chloride won't make any more solid. Well, at this point, I know my volume and molarity of sodium chloride that I had to add. I can figure out just how much sodium chloride I did add. 0.0327 liters of the sodium chloride solution, and the molarity told us that in every 1 liter of the sodium chloride solution, there was 0.15 moles of the sodium chloride, turning out to be 0.00491 mole of sodium chloride. Presuming that our observation for the solid forming was a good indicator for when we just reacted all the silver, this must have been the amount needed to just react all the silver. Our balance reaction is 1:1, so it must be just as much silver nitrate that was present. For every 1 sodium chloride, it would be 1 silver nitrate, and so there must have been 0.00491 mole of silver nitrate. By knowing the amount of sodium chloride we had to add to react with it, and using the balance reaction, we can find the amount of silver nitrate that must have been present. Well, this was in 0.1 liters, so that's all the silver nitrate that was in our beaker, but it was only in 0.1 liters. So we have our actual moles and our actual volume for silver nitrate, 0.00491 mole of silver nitrate over 0.1 liters. So 0.0491 molar silver nitrate. Realistically, our volumes are a little low on sig figs, so 0.05 molar silver nitrate. We can find what the molarity for this silver nitrate is at this actual time. For this bottle that we have, what is the actual silver nitrate that's present in it? Since the ideal concentration for antibiotics is approximately 0.088 molar, what we find is that this bottle has actually been too diluted. Instead of sticking around and evaporating over time, whoever mixed this up had added too much water. 0.05 molar is actually below the concentration that we would want if we actually had silver nitrate as an antibiotic. But we can determine what that concentration really is by using the titration method.